Okay, what we've done is we've spent 3 weeks learning the basics of physics. We've learned motion, we've learned conversions, we've learned vector addition. We've laid the foundation, excuse me, to start doing things. And today is all new material. Problem set 3 is now available. I'll try to post it tomorrow. I'm too tired to post anything right now. It's due next Tuesday, and the class will probably be half to 2/3 new material, and the rest will be review. Because next Tuesday the lecture is review. I need to double check. Oh, let me get this fixed. So Tuesday will be all review, turn in problem set 3, and then Thursday, a week from Thursday, will be test 1. I believe on Wednesday, I'll have to double check, there's a review session. I'll take a look at the room requests and see what we got. Now, a couple of quick announcements. Problem set 3, Physics 214 is aware of this. The problem set that is due the week of the test, you turn it in and it will not be returned to you in time for the test. So what you need to do is make copies and pay attention to the tutorial videos. The tutorial videos are effectively the solution set, because I do the problem. All it comes down to is just plugging and chugging, and you can do that. So problem set 3 will not be returned, but there will be stuff available. In the next 24 hours, sample test 1 will go on Blackboard. So the next 24 hours, you're going to see 2-3 tests, and so you could see what a test 1 looks like. On Thursday afternoon, we'll go over, if we have time, one of the tests. On Tuesday, we'll definitely go over one of the tests, and on the review session, we'll keep on reviewing. The Friday tutorial. Really what has happened with problem set 3 is that it is the problem set given over last summer. I knew that this was going to be a problem because the day that the baseball schedule was released, I knew that it would come into conflict with tutorials. So I have my priorities straight. I'm going to the baseball game at 2 o'clock when the gates open. Now, what's going to happen to that tutorial? I'm going to take the video from last summer that effectively does it all and post it to YouTube. So you can take a look at it. And it's really, tutorials are one of those things where I sit there and look at it and like, I've done this like countless times. I should just repost the video. I really don't like to do that because it's not interactive, but under certain circumstances, such as Ole Miss baseball, I have to make do with what I can do. So no tutorial on Friday, video only. So to briefly talk about the test and just a general overview, it's 25 multiple choice. The sample tests will have plenty of examples as to what we will cover. There will be one 5-point problem and 3 15-point problems for a total of 100% or 100 points. It's 15% of your total grade, which means it's 50% more than your entire homework score combined. So please put the effort in studying for the test rather than get overwhelmed by individual homework problems. So it is very important. The 5-point problem will be conversions. And if you see like a capital A, that's short for appetizer. Problems 1, 2, and 3. Problem 1, vector addition. 2, 2D motion. So these two are problem set 2. This is problem set 1. And then number 3, we will cover definitely by Thursday, Atwood's machine. The first test of Physics 213 that all of them, well, probably except for the first year. If you look at the past 3 years of 213 test 1s, it's the same thing over and over again. I can only test your basic knowledge. We've only been learning for 3 weeks. We only have another week and a half before the first test. So you've got to learn how to convert, how to add a vector, how to do 2D motion, and how to do an Atwood's machine. Now let's explain about Atwood's machine. Atwood's machine, with metaphysical certainty, will be on test 1. What do you mean metaphysical certainty? It will be on the test, like you breathe air. It is true. Now I understand that students taking my class, there is a segment that goes, Dr. Eschenberg's faking us out. He's totally lying. Not on the first test. The first test is a very straightforward test. You're going to sit there, and the person who comes to me and says, I didn't tell him that this was on the test, will be made an example of with great viciousness. So everything is on the test. What it comes down to, test 1 is you figuring out what does a physics test look like, and me figuring out what's your strengths and weaknesses. Now, typically, the first test comes back and it's like their strengths, not a whole lot. Their weaknesses, oh, they're everywhere. And that's to be expected. I need you guys to accept the fact that test 1, it's not going to be all sunshine and puppies. It's going to rock into, it's like a tsunami. The waves are starting to pull back, which is the indication that something big is coming. You need to be ready and face it, and you need to be, don't include your anxiety. I will not take social calls in my office, outside of office hours, for when you are freaking out. I don't know how to handle this. I have never had a student freak out in my office before. No, 3 freakouts, I call that a Monday. It's normal, it's natural. The way that you get over it, there was a student who, I'm trying to think, their hobby was like softball. And I said, tell me about the first time you ever took a pitch. She said, I looked like an idiot. And I said, exactly. What did you do to get better? I practiced, and I kept practicing. 213 test 1 is all about practice. So lather, rinse, repeat. Do the problems over and over again. The Atwood's machine will be on the test. And let me tell you the story about why Atwood's machine will always be on every single physics 213 test and final until the class collectively answers it correctly. Which means that until the end of time, Atwood's machine is going to be on the test. Now, how can Atwood's machine be on a test dealing with acoustics and pressure and gases? Let me worry about that. But it's going to be on the final. It's going to be on the tests. Get ready. So, first, enough ranting. What have we known so far? We know distance or length. We use meters. We use mass, kilograms. We use time. We use seconds. And so with these, we can do all sorts of things. Take example x equals x naught plus v naught t plus 1/2 at squared. Position is in meters. So meters, meters. Velocity, meters per second. So plus meters per second times time, seconds. Plus, I'm only interested in the units. So acceleration, meters per second squared. Time squared, second squared. So seconds cancel, second squareds cancel, and I'm left with meters, 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 which gives me meters. And so you need to become familiar with converting units, looking at equations, and doing unit checks. In our in the next demonstration, if this table was frictionless and it started to have it had initial velocity, if there's no friction, it would keep on keeping on forever and ever. So, in physics 213, an object in motion will stay in motion unless you F with it. What does he mean by F? Let's continue. An object at rest will stay at rest unless you F with it. So the question is, what is F? Force. You were thinking naughty words, weren't you? The first law of physics, Newton's first law, objects in motion stay in motion. Objects at rest stay at rest. Now we all know how I hate to write words. I'd much rather spend my time writing equations. So if I'm taking the time to write this stuff down, it's some important stuff. Excuse me, the Diet Coke is bubbly. So Newton's first law basically introduces the concept of force. Newton's second law. Force is mass times acceleration. F is equal to ma. Now, the units of m are in kilograms. The units of acceleration are in meters per second squared. So the units of force are kilograms, meters per second per second. Now this, rather than saying kilograms, meters per second, we say Newton or N. So the force times acceleration is Newton. It's also kilograms, meters per second squared. So let's do a simple example. A car or a block is experiencing a force of 10 newtons. The mass of the block is 5 kilograms. Its initial velocity is 0, so it is at rest. Question. After 10 seconds, give me its position, give me its velocity, and give me its acceleration. Now, in ballistics, AX is 0 and AY is -10. An object sliding across a surface is not ballistics. It's just an acceleration of a little block. So X in this case, since it's not moving in the Y, is X naught. We've declared that the beginning position is the origin. It's at rest, which means that the initial velocity is 0. And we have 1/2 AT squared. V is equal to V naught plus AT. Now what do we have and what do we don't have, or what do we not have? I don't know X. I do know T. I don't know A and X, and I don't know final velocity. So we in fact have 3 unknowns. In situations like this, find, now obviously I gave the problem works. It is a correctly constructed problem. So if it is a correctly constructed problem, find the variable that can be replaced. So in this particular situation, it is the A that can be replaced. What do we have? We have the mass, we have the force. If I have mass and force, I have acceleration. So F is equal to ma. F over m is equal to a. Substituting in, x equals 1/2 F over m t squared, and v is equal to F over m t. What do we know? I know F, m, and t. I don't even have to look at the other equation. I can just solve for it. F is 10, mass is 5, T is 10, so 20 meters per second. In this particular case, I don't know position, but again, I know F, mass, and time. Well, really, they should be under here, since underneath the symbol is a known quantity. So plugging this stuff in, 1/2 F is 10, mass 5, T 10 squared. So it's 1,000 divided by 10, or 100 meters. So it's at the position 100. It is at velocity 20 meters per second. And acceleration, which is F divided by m, is equal to 10 divided by 5, or positive 2 meters per second squared. So that is a one-dimensional motion problem with the addition of Newton's second law. So what we're doing is we're setting the base and we're adding a layer. Yes?
How did you get 20 meters per second?
10 times 10 is 100, divided by 5 is 20. So, okay. So what we did initially is the first steps of dealing with motion and forces. And one of the things that we're going to do now is we're going to do an incline plane. So now we have a surface, and that theta is 30 degrees. So you have a block, mass of 5 kilograms, and this distance here, that distance L is 20 meters. The initial position, or the initial velocity, is 0. It's at rest. What we're going to do is we're going to find out the time that it takes for it to reach the bottom. We're going to find the acceleration during the motion, and we're going to find the final velocity at the bottom. What I'm doing is I'm taking the base steps and applying a little bit more of a difficulty. The first thing, it was a force, there was an external force. Now, there are no external forces with the exception of gravity. The force of gravity is mg. Now in this particular case, I am using magnitudes. I'm using magnitudes because I want you to be in control of the minus signs. I don't want the minus signs to be in control of you. I want your logic to reign supreme in this. Now what we're going to do is we're going to talk about this. You can take an inclined plane and you can rotate it so that it looks like it's on a flat surface. So what we're going to do is we're going to break vectors into their component parts. This is F, FGX. This is FGY. The way that the geometry is set up, that angle is the same as that angle. So if that angle is 30 degrees, then the other angle that I've just labeled is also 30 degrees. Now, what's X and Y in this case? What we've done, if we have a rotated rest frame, that the true rest frame that we're going to do all the math in looks like this. If we simply had a mass sliding across the surface, such as in the previous problem, the X is in the horizontal and the Y is in the vertical. Just the same with this. And as the example, my niece is 8, and when she was 2, under the careful watch of her mom, my sister-in-law, I held her by the waist upside down so that she looked at the world with a different perspective, and she just kind of did that. Whoa, things are crazy. Everything is upside down, because when you're 2 years old, upside down is a big deal. And so I put her back in her chair. I didn't drop her. She took her head and then she tilted it. She wanted to recreate that perspective. She wanted to recreate that frame of reference where everything was upside down. And in this, the reference frame is at an angle. Now, one of the things that we need to introduce is the concept of Newton's third law. For every action there is an equal and opposite reaction. So what does this mean? Actually, there was a demonstration of Newton's third law. Today's Tuesday, so it had to have been yesterday. The student, if you read my Twitter, I made the announcement. Experiment 768, student attempted to pass knee through filing cabinet. It was unsuccessful. It appears that the individual seems to be in intense pain. I'm not convinced. Further experimentation and self-testing will continue. And where does that come from? We've all done this. You're wandering in the middle of the night. If you're in, those steel bed frames with the big pole coming down, and you just, with no shoes on or socks, and you just go, ow, and then expletives. That's Newton's third law. You don't have to believe in Newton's third law because Newton's third law believes in you. So with Newton's third law, I'm looking at the stapler, the water bottle, the jacket, the homework, us. What force are we under the influence of right now? The gravity of the earth pulling us down. Under all of these circumstances, gravity is working on the system. So if gravity is working on the system, why isn't the paper falling through the table? The table is pushing back. If, let's say, all our forces are down because gravity is down, and I eliminate the force on the chair that's pushing you up, you all would disappear and I could cancel class and I would be a happier individual. But there's a force pushing up on you, preventing the cancellation of class. What is that wrongful force? It is called F sub n and F sub n is the normal force. The normal force, like the name implies, it's a force. Well, what kind of force is a normal force? Well, now, I'm not normal, I'm abnormal, but that's a psychological expression. Normal in this case, when it comes to normal force, normal by definition is a vector perpendicular to the surface. So my thumb is perpendicular to the table. So it is a normal vector. Now, my thumb is perpendicular to the chalkboard. So that's the normal vector for the chalkboard. This is the normal vector on the side of my head. The vector is perpendicular to the surface right at the location of the vector. So the normal vector, or the normal force, is always perpendicular. That's the mathematical formula for perpendicular to the surface. It doesn't have to be perpendicular to the lab frame. When we look at a normal force, that normal force could be pointed in all different directions. But it's required that it's perpendicular to the surface. It has to be like that. And if it's on an inclined plane, it's still perpendicular. So the normal force is perpendicular to the surface. And if your tutor says, seriously, he repeated it 3 times? Yeah, he repeated it. Then you better write that stuff down. As my niece would say, don't do that. Remember, well, that's all she can say. She's against, whenever I chew on my pen, she says, you're going to get sick and die, so don't do that. 8-year-olds. Hysterical. So now, we've got this surface. Let's look at FGX, FGY. This is FG, and that is theta. What we have here is a right triangle. That's the theta angle. That's a right angle. It's a right triangle. So we use basic trig. Sine of theta, FGX over FG. So FGX is equal to FG, sine theta. So FGX is mg sine theta. FGY is derived from cosine theta. FGY is FG. Rearranging this, FGY is equal to FG cosine theta. So this is mg cosine theta. If that angle is theta, then that angle is theta. If that angle is theta, then those two hold true. And I'm showing you the definitions. Now, how does this relate to the normal force? The normal force on a flat surface, normal force up, force of gravity down. Up is positive, down is negative. We are declaring the signs based on their direction. We are in control. The minus signs are not in control. They are shifty and cannot be trusted. So you are the ones who are going to assign the signs. Now, what do we know about all the students in the room? This desk right here, the stapler, it's under the influence of forces. But where is it going? Someone shouted out, it's the obvious answer. It's not going anywhere. Now, granted, the 214 students, when I ask kind of a, not a dumb question, but a very simple question, the answer that I want from my students is, it's not doing anything, and how dare you ask such a simple question? And then I would sit there and respect you. Even if you said, you know what, this object is doing elephant, how dare you ask me that question? You said it wrong, but you said it with confidence. You're gonna be a future doctor or pharmacist. We patients and we customers appreciate confidence. So you're getting all sorts of lessons from this. It's not moving up. It's not moving down. What do you know about its velocity? It's 0. What do you know about its acceleration? It's 0. If it had an acceleration, it would be moving. There may be a brief moment where it comes to a stop, but then it would continue. So, in this situation, the sum of the forces in y is equal to 0. When I started teaching this course, obviously the two most important questions, or the two most important formula, are these. Dr. Eschenberg's favorite equation, Dr. Eschenberg's second favorite equation. They are fundamental to this course. The next, if I could say, I haven't really officially declared it the third favorite, Dr. Eschenberg's equation, but this equation is really important, and it is the equation of translational equilibrium. If an object is under translational equilibrium and it is experiencing forces, there must be multiple forces to keep that thing still. The sum of the forces in y is equal to 0. If you have a mass, let's say a mass was 5 kilograms. There is a force, normal force, up. There is a force down, mg. And it is in translational equilibrium. A very valid question is, on tests, is if I'm not stating it's at rest, a valid question could be, what's this thing doing initially? And if I didn't say it's initially moving or it's at rest, I have to specify. My answer is, it's not doing anything. No acceleration, no velocity. So you know that the sum of the forces in y, which is equal to ma, because Newton's second law says F equals ma, and if there are multiple forces, it's the sum of their forces is equal to ma. And that is equal to 0, which means that acceleration is equal to 0. Some would look at it and think of it as, well, that's an obvious equation. But then they truly don't appreciate what it can do for you. Because it's 0, you know that this equation is equal to the normal force minus mg. Why is normal force positive? Why does it not have a negative sign? Normal force is pointed up. Positive forces point up. Why is there a negative sign in front of mg? Downward forces are negative. In this case, g is the magnitude of gravity, so it's 10 meters per second squared. But you say, well, the force is down. Yes, the force is down from gravity. That's why that is negative. So rearranging this, mg is equal to Fn. So the normal force for an object on a flat surface is simply mg.
Where did the MA come from? Like, where did you get
Ma comes from Newton's second law. So one force F equals Ma. Multiple forces sum of the forces is equal to Ma. So if you've got more than one force acting on an object, you know that the sum of the forces is equal to Ma. And if it's not moving, then the sum of the forces, which is equal to Ma, is equal to 0. Well, let's make it a little bit complex. We're at a flat surface. Let's go on incline. That is the normal force. That is Fg. That is Fgx. That is Fgy. And we know that that is the x and that is the y, because we can rotate it like this. So what we did is we broke this vector into its components, and we all know how to do that. So now we know, do we know that there is motion in the horizontal? Do we think that this thing is going to slide downhill? Yes, because there's a force going down the hill and there is no force pulling up or pushing up the hill. Now, in terms of the y, I know that the sum of the forces in y is equal to 0. How do I know that the sum of the forces in y is equal to 0? It's not accelerating in the vertical. It's still in the vertical. It's going to move in the horizontal, but it's not going to move in the vertical. Oh, great, it's still going. So this becomes normal force minus Fgy, and Fgy is equal to normal force. Fgy, mg cosine theta. So for an object on an inclined plane where there are no other forces except for gravity, the normal force is mg cosine theta. Now, continuing on, let's sum the forces in x. Sum of the forces in x is also equal to ma, but instead of sum of the forces in y is equal to may, and ay is 0, the sum of the forces in x is equal to max, where ax is going to be non-zero. Now, what are the forces acting on the object in the x direction? Well, only Fgx. And it's pushing in the positive x direction. In the way that we've set up our axes, to the right or downhill is positive. So this becomes max is equal to Fgx, which is equal to mg sine theta. The m's cancel, and I'm left with the acceleration in the x is g sine theta. And so that is how you would determine the acceleration. You determine the normal force in the vertical, then you determine the acceleration in the horizontal. Now, x is equal to x naught plus v naught t plus 1/2 ax t squared, and vx is v naught x plus at. In this particular case, we stated that the object was at rest. So those are 0. We also stated that the initial position was 0. We set the origin to be the top of the hill. So we now know x, that's 20. Did I say it was 20? Let's just say it's 20. I don't want to dig through it. X is equal to 20, so it's 20 meters down the hill. I think it was 20. A is g sine theta. Is that right? Okay. I know A, x, that's g sine theta. And I don't know t. And I don't know final v sub x. So which equation do we attack first? The left one. Why? Only has one unknown. (2x over ax is equal to t squared. Square root of 2x over ax is equal to t. So t is the square root of 2x over g sine theta. 2 times 20, g is 10, sine is 30. Now, one of the shortcuts that I frequently do is sine of 30 degrees is 0.5 exact. So 10 divided by 0.5 in the denominator is 5. 40 divided by 5 is 8. So the square root of 8 is 2.83 seconds. Now, in the other case, time is now a known quantity. A, g sine theta, t is known. So this becomes 10 sine 30 times 2.83. 10 sine 30 is 5. 5 times 2.83, 14.14 meters per second. And so that is the final velocity. The acceleration, while we're at it, is just g sine theta. So 10 sine 30, or 5 meters per second squared. So if we were to plot the position, the velocity, and acceleration x started at 0. The velocity started at 0. The acceleration started at positive 5 meters per second squared. And it was always 5 meters per second squared. It will always be a constant. It will either be 0 and unchanging or non-zero and unchanging. Now, velocity starts out at 0 and it steadily increases. That's a linear equation. So the velocity looks like this. The slope of this line is 5. Now time, what I'll do is the dotted line will be at time equals 2.83 seconds. The position, the initial velocity starts off slow and then it increases. So what it does is it bows up like this because it's more of a quadratic formula. And so this position is 20 meters. So there is the plot, and that's how the plots look. Yes?
Is A always G sine 30, or do we figure that out?
It depends on the situation. As we make it more complex, the acceleration in y and x are going to get stranger. What I'm trying to do is, we've got to walk before we start running. The problem set will have you sprint. So what we're doing is we're taking the basic equations and then we're going to build on them during the problem set. Take a look at the tutorial that's going to come out. I'll try to post it tomorrow because we're not going to tutorial on Friday. And so then you can get started early on problem set 3. All right, next. Friction. When I threw the sweater or sweatshirt across the table, it slowed down. And why is that? Because of friction. The two surfaces, if you take your hands and you rub them together, or you take your hand and put it on like a rough surface, you can feel the surface catching on your skin and then releasing your skin, and then it catches again somewhere else. What's happening is that the material and your skin are briefly not bonding together, but sticking. And it's the macro property of how this thing sticks when two surfaces rub against each other. Unless I say so, or unless I say no friction, there will be friction. In the problem set, you will see a symbol looking like this. That's a mu. That's a lowercase Greek m. Now, there are two types of friction. There is static and there is kinetic. For static friction, there is no motion. For kinetic, there is motion. So as an example, if I put my hand down and lightly push it, it sticks. That is an example of static friction. If it's sliding like this, it's kinetic. So if there is motion and you use static friction, doom. If it's standing still and you use kinetic, once again, doom. So pay attention to, is it moving or not? If If it is moving, kinetic. If it is not moving, static. This mu changes based on the situation. Static is mu sub s, and kinetic is mu sub k. Now, what is the relationship between... There is a relationship between friction force and normal force. If you know its normal force and you know its coefficient of friction, you will know its friction force. The friction force, which, if we're using static, I use F sub s is equal to mu sub s times normal force. If it's kinetic, mu sub k times normal force. So in both cases, the normal force is being used for static and for kinetic. These mu's will be given, or you will solve for them. So the mu's will either be given or you will solve for them. Now, when we have an object simply sliding across a flat surface, let's say it started at 0 with a velocity of initial of 20 meters per second. What I want to know is if mu sub k is equal to 0.4, where does it stop? And give me the time. If at 0 the time is 0. So first, do I need to know anything about the coefficient of static friction? No. The object is clearly moving. Another question is, what are the units of mu? Mu sub k and mu sub s, that doesn't matter, it's the same. When we do F is equal to ma, the newtons of force, or the units of force, is mass, kilograms, acceleration, meters per second squared. And so those are the units of force. For these equations here, mu sub s is the static friction force divided by the normal force. Static friction force is in newtons. Normal force is also in newtons. So they cancel. Mu sub s is unitless. Now it could be used, you could write it as newtons over newtons, or kilograms meters per second squared over kilograms meters per second squared, but you know that those batches of units cancel each other out and you're left with nothing. Just a number, a raw number. These numbers are studied by material scientists, low friction, mu is close to 0, high friction, typically would be, anything with friction, 0.5 and up. Mu is typically, well, obviously it's a unitless number, if there is friction, I tend to make it a fraction, like 0.2 or 0.8. It's rarely greater than 1. If there is no friction, and you guys need to start, I'll be so happy with you if you start doing this. I had Jason Bell, who was the starting right guard, I think, or left guard for the football team, and I taught him Physics 213. And so I would say, and they would ask, is there friction? And I would say, there is no friction. And then Jason Bell would go, yay, no friction. When I say there is no friction, you all should be very cheerful. If there is no friction, mu sub k or s is equal to 0. So if there is no friction, yay, no friction, mu sub k or s is 0, so friction force is 0. And you don't have to worry about finding friction force. But in this problem, we do. Boo, friction. Well, when we're doing this, there is, just as there was a ritual, a set of actions that you do to add a vector, break them, add them, recombine. Just as you have two-dimensional motion in their actions, write out x equals x naught plus v naught xt, and y equals x y naught plus v naught yt plus 1/2 ayt squared. It's burned into my brain. What you need to do is, if you say it 5,000 times, your brain will say, I've had enough, I know it now. And then that's what you guys need to do. Now granted, the equations will be on the test, but how you use them is up to you. The first thing you do with these objects when there's friction, even when there's not friction, you sum the forces in y, which is equal to 0. And the product of this is going to be the normal force. So down is Fg, up is F normal. It's not moving in the horizontal, so it is in translational equilibrium, which means that the sum of the forces in y are equal to 0. Normal force is up, gravity force is down, so gravity force is equal to normal force. Fg is mg. So the normal force is equal to, mass of the object is 5. 5 times 10, or 50 newtons. There's 50 newtons of force from the surface on the block. There's 50 newtons of force on the block, or from the block on the surface. Or 50 newtons of force from the earth on the block. Now that we have normal force, that's step 1. Stage 2 is find friction force. Skip if mu sub k or s is equal to 0. So if mu sub k is 0, or I say it's frictionless, mu sub k or mu sub s is 0, and you go, there's no friction force. But in this case it is. So friction force is equal to mu sub k times normal force, which is 0.4 times 50, or equals to 20 newtons. That is the friction force. Now let's talk about the direction of this friction force. Gravity points down, obviously. Normal force points perpendicular. Friction force always points in the opposite direction of the velocity vector. So the velocity is to the right. So the friction force vector points to the left. So if we were to write it as a polar angle, the friction force would be 20 newtons at 180 degrees. The friction force is always opposite of velocity. Velocity to the right, friction force to the left. Velocity to the left, friction force to the right. Because it just, I mean, that's what friction does. Friction opposes motion. Friction slows it down. Friction removes energy from the system. We'll get into that for test 2 material. So now we have friction force. Step 3, find A. These 3 steps are the same for object on a flat surface, object on an inclined surface, and then this is the picture of an Atwood's machine. All 3 use these 3 steps. What I'm teaching you are the procedures. I'm not teaching you to catch a specific fish. I'm teaching you how to fish in the most general terms. Now, for finding A, you sum the forces in X, which is equal to MAX, which is not equal to 0. This object is moving in the x-axis. So what happens is this force is to the left. So it is minus friction force. The friction force is to the left. The minus sign is there. So it's got to be negative. So AX is minus F sub F, and M, friction force is 20, mass is 5, so acceleration is 4 meters per second squared, negative. Does a negative value for this particular problem make sense? Yes, because it's moving to the right, it's slowing down, so the acceleration vector is opposite that of velocity. If acceleration and velocity are opposite, it will slow down. If acceleration is in the same direction as velocity, it will speed up. Next, x equals x naught plus v naught t plus 1/2 at squared. And that's ax. And vx is v naught x plus ax t. So we're doing everything in the horizontal. The initial velocity is 20 meters per second. So we know that. We know A is -4. I know what the initial velocity in x is, that's 20. My x naught, I know that's 0. I don't know x and t. Do I know the final velocity? So the question is, actually that's probably, where, oh, I've written it down. Where does it stop? It's 0. When it comes to a stop, the velocity is 0. So that goes away and that's 0. One equation, 2 unknowns, time and position. One equation, 1 unknown, time is solvable. So minus v naught x over a, or I'm sorry, let me do it step by step. That comes over here. Is t. So negative V naught X is negative 20. A is negative 4. So T is 5 seconds. So this thing will come to a stop in 5 seconds. The last thing that we're going to do is calculate the final position. I now know time. I can solve for this. 20 times 5 plus 1/2 minus 4, 5 squared. So negative 2 times 25 is negative 50. 20 times 5 is 100. So the final position is 50 meters. So that's where it comes to a stop. Remember, sum the forces in Y first to get normal force. Find friction force next. You can skip it if the coefficient of friction is 0. Next, find A. And then if there is a 4, normally I don't write 4, but 4 makes sense. Solve for my 2 favorite equations. Those are the steps. Everything that we do for the next week are gonna be those 4 steps. Learn them, love them. See you on Thursday.